At first glance, it is the most ordinary object in your refrigerator, a simple container meant to be used once and discarded. But the modern aluminum beverage can is one of the most sophisticated pieces of engineering on the planet. To hold the pressure of a carbonated drink while remaining incredibly thin and light requires physics pushed to the absolute limit. Every year, over 180 billion cans are manufactured, each one a testament to high-speed precision. We're talking about a wall thickness of less than 100 micrometers. That is thinner than a human hair, yet it can support the weight of a full-grown adult. Creating this requires a brutal transformation of raw metal through a process known as deep drawing and ironing. It is a journey from a thick, flat disc to a high-performance pressure vessel in less than a second. This is not just a container. It is a masterclass in material science and mechanical deformation. To understand how it is built, we have to go back to the source, to the high-strength alloys that make this impossible geometry a reality. Get ready to dive into the world of cold working, molecular alignment, and the relentless speed of the modern assembly line. It all begins with a massive coil of aluminum alloy, specifically the 3104 series. This isn't pure aluminum. Pure aluminum is too soft. To survive the stresses of the manufacturing process, it is alloyed with magnesium and manganese. These elements provide the structural integrity needed for the can to maintain its shape under 5 to 90 pounds per square inch of internal pressure. These coils can weigh over 30,000 pounds and stretch for miles. The metal is rolled to a very specific thickness, precisely 0.285 millimeters. Before it even enters the factory, the surface is coated with a thin layer of lubricant to prevent the metal from tearing or sticking during the violent shaping process ahead. The chemistry must be perfect. If the grain structure of the metal is off by even a fraction, the can will fail. We are looking for a balance between ductility, the ability to be stretched, and strength. Every square inch of this metal is inspected by laser systems to ensure there are no microscopic defects. In the world of high-speed manufacturing, a single impurity can cause a catastrophic blowout on the line, halting production that runs at 2,000 units per minute. This is the foundation upon which everything else is built. The manufacturing journey starts with a massive machine called a cupping press. This beast of a machine exerts tons of force to perform two tasks simultaneously, blanking and drawing. First, a circular disc, called a blank, is punched out of the aluminum sheet. This disc is about 5.5 inches in diameter. Immediately after the cut, a high-pressure punch pushes the disc through a circular die. This is the drawing stage. In a fraction of a second, the flat disc is transformed into a shallow cup. It looks like a small tuna can. This process is critical because it begins to align the molecules of the aluminum. The metal isn't being cut into this shape, it is being forced to flow. The lubricant we mentioned earlier is doing heavy lifting here, reducing the friction between the punch and the die to near zero. If the metal gets too hot from friction, it will weld itself to the machine. But instead, the aluminum slides, conforming to the shape of the die. The result is a starter cup with a consistent wall thickness. At this stage, the walls are still relatively thick, but that is about to change as we head into the most violent and impressive part of the process, the body maker. Now we enter the body maker, where the physics really gets interesting. This involves a process called ironing. The shallow cup is placed onto a precision-machined tungsten carbide punch. This punch moves at incredible speeds, driving the cup through a series of 3 progressively smaller ironing rings. Think of it like a rolling pin stretching out dough, but in 3 dimensions. As the cup passes through each ring, the gap between the punch and the ring is smaller than the thickness of the aluminum. This forces the metal to stretch upward. The walls of the can are thinned out by nearly 60%, while the bottom of the can remains at its original thickness for strength. This is cold working. By physically stretching the metal at room temperature, we are actually making the aluminum stronger. The molecular structure is being elongated, creating a grain that runs vertically along the can wall. This allows the can to be incredibly thin, just 0.07 millimeters thick in some places, while still being able to withstand the massive pressure of the carbonated liquid inside. It is a delicate balance of speed, force, and lubrication, all happening in less than 1/5 of a second. While the walls are being ironed thin, a critical feature is being formed at the bottom of the can, the dome. If the bottom of a can were flat, the internal pressure of the beverage would cause it to bulge outward, making it unstable and likely to burst. To solve this, the body maker uses a domer. As the punch reaches the end of its stroke, it presses the bottom of the can against a convex tool, creating an inward curving dome. This shape is an engineering stroke of genius. It uses the geometry of an arch to distribute the internal pressure of the gas toward the stronger, thicker edges of the base. This dome allows the can to withstand up to 90 pounds per square inch of pressure without deforming. It effectively turns the bottom of the can into a high-strength pressure vessel. Without this specific curve, the can would have to be much thicker and much heavier to survive. Every time you see that curve at the bottom of your drink, you are looking at a structural element that allows for the extreme lightweighting of the modern can. It is a perfect marriage of form and function, calculated to use the least amount of metal for the maximum amount of strength. After the ironing process, the can is now the correct height, but the top edge is ragged and uneven. This is due to earing, a phenomenon where the metal stretches slightly differently depending on the direction of the grain. To fix this, the can enters a trimmer. A stationary blade holds the can in place while a circular knife spins around the top, shearing off the excess metal to create a perfectly clean straight edge. These trimmings aren't wasted. They are vacuumed up and sent immediately back to the smelter to be recycled into new coils. Once trimmed, the cans move to a massive multi-stage washer. During the drawing and ironing, the cans were covered in lubricants and metal fines. They must be chemically cleaned and deionized before anything else happens. The cans travel through a series of acid and deionized water baths to remove all traces of oil and impurities. This produces a pristine, shiny aluminum surface that is ready for the next critical step, coating. If the surface isn't perfectly clean, the inks and protective liners won't stick, which could lead to the metal reacting with the liquid inside, something we must avoid at all costs. Aluminum is a highly reactive metal. If you put a soda, which is acidic, directly onto raw aluminum, it would eventually eat through the metal and ruin the flavor. To prevent this, every single can receives an internal protective liner. This is a thin layer of organic coating, usually a water-based epoxy or polyester, sprayed into the interior as the cans spin at high speed. The spray nozzle must ensure 100% coverage, because even a microscopic pinhole could lead to a leak or off flavors. This coating is only a few microns thick, so thin you can't even feel it, but it acts as a critical barrier between the beverage and the metal. Once sprayed, the cans pass through a curing oven where the heat hardens the liner into a smooth glass-like finish. This is one of the most strictly controlled parts of the process. Quality control sensors use high-voltage electricity to test the integrity of this liner. If even a tiny amount of current passes through the wall, it means the liner is compromised, and the can is instantly rejected. This invisible shield is what allows beverages to have a shelf life of months or even years without losing their quality. Now it's time for the can to get its identity. The printing process for aluminum cans is a marvel of rotary engineering. Standard printers apply one color at a time, but in a can plant, all colors are applied at once in a process called offset deco printing. A central blanket wheel picks up different colored inks from multiple plates, up to 6 or 8 colors, and transfers the entire image onto the spinning can in a single rotation. This happens at speeds of over 2,000 cans per minute. It is a blur of motion. After the ink is applied, a clear over varnish is added to protect the graphics and provide a smooth surface for the cans to slide against each other on the filling lines. The cans then travel through a long oven to bake the ink and varnish, ensuring they are dry and scratch resistant. The precision required here is staggering. Every dot of ink must align perfectly to create the crisp logos we see on the shelves. One slight misalignment and thousands of cans would be misprinted before the operator could even hit the stop button. It is a high-stakes environment where machine timing is everything. The can is almost finished, but the top is still wide open. If we try to put a lid on it now, the lid would have to be the same diameter as the body, which would use too much metal. To save material and increase strength, the top of the can is necked in. This is done in the necker, a machine that uses a series of 17 separate dies to gradually reduce the diameter of the top opening. You can't do this in one step, or the thin aluminum would wrinkle or collapse. Each die gently pushes the metal inward, a fraction of a millimeter at a time, until the signature tapered neck is formed. After the necking is complete, the very top edge is bent outward to create a flange. This flange is what the beverage filler will eventually fold over to lock the lid or end onto the body. This is the final shaping of the can body. It is now a lightweight, high-pressure capable vessel, ready to be palletized and sent to a filling plant. Millions of these are produced every day with zero variants. The engineering required to achieve this consistency at such high volume is nothing short of a miracle of modern manufacturing. Before any can leaves the factory, it must pass through an eye scanner. High-speed cameras and light sensors inspect every millimeter of every can. They look for infinitesimal pinholes, dents, or imperfections in the printing. Any can that fails is blasted off the line with a jet of air, destined for the recycling bin. And that leads to the most impressive part of the aluminum can story, its life cycle. Aluminum is infinitely recyclable. Melting down a used can takes only 5% of the energy required to create new aluminum from ore. In fact, a can you put in a recycling bin today can be back on a store shelf as a brand new can in as little as 60 days. The physics of deep drawing and ironing, the chemistry of the alloys, and the precision of the high-speed machinery all work together to create a product that is both an engineering masterpiece and a sustainable solution. Next time you crack open a cold drink, take a second to look at that thin-walled cylinder. You are holding a product of intense pressure, molecular manipulation, and one of the most efficient manufacturing processes ever devised by man. It is a simple object, born from complex physics. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this tech archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.